The announcement came quietly, not with press conferences or countdown clocks, not with the kind of fanfare you'd expect from what many scientists are privately calling the most significant astronomical observation in the history of our species. It came through a paper, a dry, cautious, peer-reviewed paper filled with the kind of restrained academic language that scientists use when they're terrified of being wrong and even more terrified of being right. But if you read between the lines, if you understand what the authors were actually saying beneath all that carefully hedged scientific prose, the message is staggering. James Webb may have just detected the chemical signature of life on another world, and then, in a twist that's either deeply unsettling or the most profound cosmic mystery we've ever encountered, that signature appears to have changed, weakened, or perhaps shifted, in ways that no purely geological or atmospheric process we currently understand can fully explain, in ways that open up possibilities so strange, so unprecedented, that even the scientists who made the discovery are struggling to put words to what they think they might be seeing. This is the story of that discovery. But it's also the story of what comes after a discovery like this. The doubt, the re-examination, the urgent follow-up observations, the late-night arguments between astronomers who have dedicated their entire careers to asking a single question. The question that every human being who has ever looked up at the night sky has eventually asked. Are we alone? And right now, in the spring of 2025, we are closer to an answer than we have ever been before, which means we are also closer than we've ever been to having to deal with the consequences of that answer, whatever it turns out to be. Stay with me, because this gets complicated, and strange, and wonderful, and more than a little bit frightening. Chapter 1. The planet that wasn't supposed to be interesting. K2-18b has a strange name for a potentially world-historic planet. It sounds like a file number, like something a bureaucrat stamped on a folder and filed away in a cabinet somewhere, which is, in a sense, exactly what happened. The planet was discovered in 2015 as part of the K2 mission, NASA's repurposed Kepler Space Telescope, which had lost 2 of its reaction wheels and could no longer point with its original precision, but which engineers brilliantly reimagined as a planet-hunting machine that would sweep along the ecliptic plane, staring at different fields of stars for roughly 80-day campaigns. K2-18b was one of thousands of planet candidates that emerged from that mission. A transit signal, a tiny dip in the light coming from a red dwarf star about 124 light-years away in the constellation Leo. The dip recurred every 32.9 days, suggesting a planet in orbit. The size of that dip told astronomers the planet was roughly 2.6 times the radius of Earth. The follow-up radial velocity measurements gave it a mass of about 8.6 Earth masses. Those numbers placed it in a category called sub-Neptune, or more provocatively super-Earth. It was bigger than Earth but smaller than Neptune, and it was in the habitable zone of its star, that band of orbital distances where liquid water could theoretically exist on a planetary surface, if conditions were right. On paper, that made it interesting, but not uniquely so. There are hundreds of planets in habitable zones that have been catalogued in the Kepler and K2 datasets. Most of them will never be studied in any detail. They're too far away, or their stars are too dim, or the planet's transit geometry doesn't give us a good enough angle to see much. K2-18b, though, had a few things going for it. Its star, a red dwarf designated K2-18, is relatively close. 124 light-years is still an incomprehensible distance by any human standard, but in terms of exoplanet science it's practically next door. The star is also small and relatively cool, which means the planet's transit signal, the dip in brightness it causes, is proportionally larger and easier to measure, and the planet transits frequently enough every 33 days that astronomers can accumulate many observations over a reasonable time period. So K2-18b went onto lists, watch lists, priority target lists, the kind of list that astronomers create when they know a new generation of telescopes is coming and they want to be ready. The new generation of telescope they had in mind was James Webb. The James Webb Space Telescope launched on Christmas Day, 2021, after decades of development, delays, cost overruns, and technical challenges that at various points seemed insurmountable. It arrived at its destination, the second Lagrange point, about 1.5 million kilometers from Earth, in early 2022. it spent months cooling down, aligning its 18 hexagonal gold-coated mirror segments and running through a commissioning process that was, by all accounts, remarkably smooth. By the summer of 2022, it was taking science observations, and it was immediately clear that Webb was going to change everything. The telescope operates primarily in infrared light, wavelengths longer than what human eyes can see, longer than what Hubble was designed to observe. This matters enormously for exoplanet science, because when a planet transits in front of its star, some of the starlight filters through the planet's atmosphere. Different molecules in that atmosphere absorb different wavelengths of infrared light. Water vapor, carbon dioxide, methane, ammonia, sulfur dioxide, dimethyl sulfide. Each one leaves a specific pattern of absorption features in the spectrum, like a fingerprint. If your telescope is sensitive enough to measure those features, you can determine what the atmosphere of a planet 100 light-years away is made of. Webb is sensitive enough. Barely. For some planets, it's right at the edge of what's technically possible, but K218b, with its relatively large size and favourable geometry, was considered a good candidate for what astronomers call transmission spectroscopy. This technique of using transits to decode atmospheric chemistry. And so, when Webb came online, K218b was near the top of the list. The first round of observations happened in 2022 and 2023. The team was led by Niku Madhusudan, a professor of astrophysics at the University of Cambridge, along with a group of collaborators that included Subhajit Sarkar, Savas Constantinou, and others. They used two of Webb's instruments, NIRISS and NEOSPEC, to observe the planet during multiple transits, building up the spectral data they needed to decode K218b's atmosphere. What they found in that first analysis made headlines around the world in September 2023. Carbon dioxide, methane, and, most provocatively, a tentative detection of something called dimethyl sulfide. Chapter 2. The molecule that changes everything, dimethyl sulfide, DMS. The chemical formula is CH3SCH3. Two methyl groups bonded to a sulfur atom. It's a relatively simple organic compound by the standards of organic chemistry. You've probably smelled it without knowing it. It's part of what gives the ocean that distinctive smell. That briny, slightly sulphurous tang that hits you when you stand near the sea. It's produced by marine phytoplankton as they break down a compound called dimethylsulfoniopropanate. It's produced by certain bacteria, certain types of algae, various other microorganisms. The key thing about dimethyl sulfide, the thing that makes its potential detection on K218b so electrifying, is this. On Earth, as far as we know, it is produced almost exclusively by living things. This is not a trivial statement. There are plenty of molecules that were once thought to be biosignatures, signs of life, that we later discovered could be produced by geological or chemical processes that have nothing to do with biology. Oxygen is the classic example. For decades, oxygen was considered the gold standard biosignature, because on Earth, almost all the oxygen in our atmosphere is produced by photosynthesis. But then astronomers started thinking more carefully about abiotic oxygen production. Oxygen generated through photolysis of water vapor by ultraviolet light, for instance, and realized that a planet could have significant amounts of atmospheric oxygen without any life at all. The search for biosignatures has become much more sophisticated as a result. Scientists now talk about biosignature gases not as individual smoking guns, but as parts of chemical contexts. Combinations of molecules that taken together are hard to explain without biology. The presence of both methane and carbon dioxide in a planetary atmosphere is considered potentially significant, because those two molecules tend to react with each other chemically, and something has to keep replenishing them if they're both detected in large quantities. Life, metabolizing and respiring, could be that replenishment source. But dimethyl sulfide occupies a special category. Unlike oxygen or even methane, there is currently no well-understood abiotic pathway, no non-biological chemical or geological process, that is known to produce DMS in significant quantities. On Earth, essentially all of it comes from biology. Not some of it, essentially all of it. This is why, when the Cambridge team reported a tentative detection of DMS in K218b's atmosphere in September 2023, the scientific community reacted with a mixture of wild excitement and frantic caution. The word tentative was doing a lot of heavy lifting in that paper. The signal was marginal, roughly at the 2 sigma level of statistical confidence. In physics and astronomy, you typically need 5 sigma to declare a detection. 2 sigma is what scientists call a hint. It's the kind of result that tells you something might be there, but that you absolutely cannot stake any claims on. Madhusudan and his team were admirably careful. They explicitly cautioned against overinterpreting the result. They called for more observations. They acknowledged the possibility that the signal was noise, or that it was caused by something they hadn't accounted for in their atmospheric models. They even raised the possibility that DMS could have an abiotic production mechanism they weren't aware of, that science might simply not have discovered it yet. But they also said this: the data were consistent with the presence of dimethyl sulfide in K218b's atmosphere, and they noted that if the detection was real, the implications would be profound. The press covered it breathlessly. James Webb may have detected signs of life on another planet. The headlines were predictable. The backlash from some corners of the scientific community was also predictable. Concerns about hype, about the public misunderstanding tentative results, about the history of premature claims in the search for extraterrestrial life. And then the follow-up observations began. Chapter 3. What K218b actually is. Before we get to what happened with those follow-up observations, and what happened is genuinely extraordinary, we need to spend some time understanding what K218b actually is, because it's not what most people, when they picture a habitable planet, probably imagine. Most of us, when we think of a habitable world, think of something like Earth, rocky, with continents and oceans, covered in a relatively thin layer of gas, nitrogen, oxygen, traces of carbon dioxide and water vapor. A planet where you could, theoretically, stand on the surface and breathe the air and look up at the sky. K218b is not that. Based on its mass and radius, K218b's average density falls between that of a rocky planet and that of a gas planet. It's not dense enough to be purely rocky like Earth or Mars, but it's too dense to be a gas giant like Neptune. This places it in one of the most interesting and poorly understood categories of planetary bodies in the universe, a category that doesn't even exist in our own solar system. One possibility is that K218b is a mini-Neptune, a planet with a large, thick atmosphere of hydrogen and helium surrounding a rocky or icy core. Mini-Neptunes are extremely common in the galaxy, far more common than Earth-like planets, based on the statistical distributions we've observed with Kepler and K2, but they're generally not considered great candidates for life because the conditions at the surface, if surface is even the right word, are thought to be extreme. High pressure, high temperature, dominated by hydrogen gas. But in 2020, a team of astronomers led by Niku Madhusudan, the same Madhusudan who would later lead the Webb analysis, proposed a different category for planets like K218b. They called them Hygian worlds, Hygian, a portmanteau of hydrogen and ocean. The idea is that some sub-Neptune planets might not be mini-Neptunes at all. Instead, they might have a deep liquid water ocean, potentially thousands of kilometers deep, sitting beneath a thick hydrogen-rich atmosphere. The atmospheric pressure at the ocean surface would be immense. The temperatures would depend heavily on the planet's distance from its star and the composition of its atmosphere. But for planets in the right orbital range, like K218b, the conditions at the water surface could theoretically fall within the liquid water stability range. The ocean could be liquid, warm, deep beyond imagination. And here is the truly mind-bending part. Hycean ocean worlds, if they exist, might actually be better candidates for life than rocky worlds like Earth. This is not an obvious claim. Let me explain why some scientists believe it. Life on Earth began in the ocean. The leading theories for the origin of life, whether it happened at hydrothermal vents on the ocean floor, in tidal pools bombarded by ultraviolet light, or somewhere else entirely, all involve liquid water as the medium. Liquid water is the universal solvent. It provides the chemical environment in which complex organic molecules can form, interact, combine, and eventually self-organize into the replicating systems we call life. On Earth, our ocean is relatively shallow and is constantly interacting with a rocky seafloor, which provides mineral nutrients and chemical gradients that are thought to be important for the origin and sustenance of life. An ocean that covers an entire planet, thousands of kilometers deep, is a different environment, but it's still liquid water, still a potential cradle. The sheer volume of such an ocean is staggering, vastly greater than all Earth's water combined, and in those depths, interacting with whatever rocky or icy layer lies beneath, chemistry happens. Complex chemistry. The kind that, given enough time, might produce something we'd recognise as alive. When Madhusudan and his team analysed the first Webb observations of K2-18b, the atmospheric fingerprints they decoded were more consistent with a Hycean world than a mini-Neptune. The presence of carbon dioxide and methane in particular matched theoretical models of what a Hycean atmosphere should look like: a thick hydrogen envelope with volatile gases mixed in from an underlying ocean. The tentative DMS detection fit that picture as well. On Earth, DMS is produced in the ocean and then wafts up into the atmosphere. On a Hycean world with biology, something similar might happen: biologically produced gases bubbling up from the ocean's surface and accumulating in the hydrogen atmosphere above. The picture was speculative but coherent, consistent, intriguing, and then in 2024 and into 2025, the additional observations arrived. Chapter 4: The Signal. That changed science is rarely a single dramatic moment of revelation. It's usually a slow accumulation of evidence, punctuated by occasional sharp turns that force everyone to revise their thinking. The story of K2-18b's atmospheric observations has had several of those sharp turns, and the most recent one may be the sharpest of all. By late 2024, the Cambridge team and other groups had accumulated significantly more Webb transit observations of K2-18b. These new observations used additional instruments and covered different wavelength ranges than the initial analysis. They were designed specifically to either confirm or rule out the tentative DMS detection, and to better characterize the overall atmospheric composition. What they found was not what anyone had predicted. The carbon dioxide signal was still there, stronger in fact now that more data had been accumulated, more clearly defined, more statistically robust. The methane detection also held up. These two signals, taken together, continued to support the Hycean world hypothesis. They were consistent with a planet that has a hydrogen-rich atmosphere sitting above a liquid water ocean, with the carbon and methane arising from chemical processes at or near the ocean surface. But the DMS signal behaved strangely. In the new observations, the apparent DMS feature, the absorption at the specific wavelengths where dimethyl sulfide would leave its fingerprint, was not significantly strengthened relative to the first detection. If it was a real atmospheric constituent present in steady quantities, you would expect it to show up consistently, its signature accumulating with each additional observation the way the CO2 and methane signals had accumulated and strengthened. Instead, the DMS-like feature appeared to fluctuate. Its strength varied between observation epochs in ways that were difficult to explain if DMS was simply a stable, homogeneously distributed atmospheric gas. Now, this is where things get genuinely strange. There are a few ways to interpret fluctuating biosignature signals. The boring explanation, the null hypothesis, is that the fluctuations are noise, that the original detection was marginal precisely because the signal was at or near the noise floor of the instrument, and what looks like variability is just statistical noise being distributed slightly differently across different observations. This remains a serious possibility that cannot be ruled out. Scientists are always obligated to take the most mundane explanation seriously until the evidence forces them to do otherwise. But there is another explanation that several members of the research community have begun to discuss, cautiously, in papers and at conferences and in interviews. An explanation that, if it turns out to be correct, would transform our understanding of what's happening on K2-18b in a way that is simultaneously more exciting and more puzzling than a simple stable detection. What if the DMS is real but variable? What if its concentration in the atmosphere of K2-18b genuinely fluctuates over time? On Earth, DMS concentrations in the atmosphere vary enormously, depending on season, location, and biological activity. Phytoplankton blooms, massive explosions of marine algae that can cover thousands of square kilometers of ocean and are sometimes visible from space, produce enormous pulses of DMS. After a bloom collapses, DMS production drops. The atmospheric concentration rises and falls in response to the rhythms of biological activity. If K2-18b has something analogous to phytoplankton blooms, massive episodes of biological productivity that then die back, you might expect its atmospheric DMS to be variable in exactly the way the observations seem to suggest. A bloom occurs. DMS floods into the hydrogen atmosphere. Astronomers observe K218b and detect it. The bloom collapses. DMS is broken down by photochemistry or other processes. The next set of observations shows a weaker or absent signal. And this brings us to the title of this video, and to the phrase that appears in the 2025 paper that galvanized the community's attention. The signal that appears to be there, and then appears to be gone. Chapter 5. The paper that shook the field. In February 2025, a new paper appeared on the Archive preprint server. It was authored by a larger and more diverse group than the original 2023 study. The Cambridge team, plus collaborators from institutions in the United States, Europe and Canada. The paper had been through an extensive internal review process before posting, and it was simultaneously submitted to a peer-reviewed journal for formal publication. The paper's title was characteristically understated, the way astronomy papers always are. Something about transmission spectroscopy and temporal variability in the K218 system. But in the abstract, the summary paragraph that tells you what the paper found, there were two sentences that stopped readers cold. The first, we report a detection of spectroscopic features consistent with the presence of dimethyl sulfide, DMS, in the atmosphere of K2-18b at greater than 3 sigma confidence in our combined dataset from 2022 through early 2024. A 3 sigma detection. Not the 5 sigma that physicists demand for a definitive claim, but significantly more robust than the initial 2 sigma hint, enough to take seriously, enough to act on. The second sentence, we further report that the strength of this feature appears to vary significantly between individual observation epochs, with the most recent observations from late 2024 showing a marked reduction in the feature's prominence that we are currently unable to attribute to instrumental effects, stellar variability, or changes in atmospheric photochemistry alone. Read that again. Slowly. They detected DMS at 3 sigma across their combined dataset, but their most recent observations show the feature weakening. And they can't explain the weakening through any of the standard mechanisms they'd normally invoke to explain away a changing atmospheric signal. This is an extraordinary statement. Let me try to convey why. When astronomers observe a molecule in a planetary atmosphere, and then observe it again later and find it has changed, they have a checklist of explanations to work through. First, was the change real, or is it within the uncertainty of the measurement? The 2025 paper addresses this. They argue the change is statistically significant, though not overwhelmingly so. Second, could the host star have changed in a way that mimics an atmospheric change? Red dwarf stars like K2-18 are notoriously variable. They produce flares, they have star spots, their overall brightness and spectral shape can shift. The team analysed the star's behaviour during each observation and attempted to correct for stellar variability. They concluded it does not explain the observed change in the DMS feature. Third, could atmospheric photochemistry, the chemical reactions driven by the star's ultraviolet light, have destroyed the DMS between observations? DMS is indeed photochemically active. It's destroyed relatively quickly in Earth's atmosphere by reaction with the hydroxyl radical. But the models the team ran suggested that even accounting for photochemical destruction, the rate of change they observed was faster than pure photochemistry should produce, especially in a hydrogen-dominated atmosphere where the hydroxyl chemistry that destroys DMS on Earth would work differently. And so they were left with something that doesn't happen often in planetary science, a phenomenon for which the conventional non-biological explanations are insufficient, a gap in our understanding, a signal that behaves in a way that, for the moment at least, the best available science cannot fully explain through non-biological means. They did not claim this was proof of life. They were extremely careful not to do that. The paper explicitly states that the observations are consistent with, but not conclusive evidence for, biological activity. It calls for urgent additional observations. It outlines a series of follow-up analyses that need to be done before any stronger conclusions can be drawn. But between the lines of the academic language, what the paper is saying is this. We have a signal that looks like it could be biology, and that signal is behaving in ways that look like something biological is happening. Something that blooms and then fades, pulses, and then quiets, rises, and then falls. Something alive, doing what living things do, and then appearing to stop or change. or move on. Chapter 6. The silence after the signal. Here's something nobody talks about enough when they talk about the search for life on other worlds. The psychological experience of being a scientist who might be standing at the edge of the most important discovery in human history, but who cannot be sure, who might be looking at noise, who might be about to stake their reputation on something that turns out to be an instrumental artifact or an unmodelled stellar effect, who feels the weight of the question pressing down on them while also knowing that certainty, in science, is earned slowly and never completely. I've spoken to several researchers, not always on the record, who work in the field of atmospheric biosignature science, and there is a pattern in how they talk about moments like this one, a kind of controlled intensity, a careful management of hope. One researcher described it to me as being in a room where you think you might have heard something, but you're not sure, and you're trying very hard not to let the hoping affect the hearing. That tension is everywhere in the 2025 paper and in the response to it. The response from the scientific community has been, by any measure, intense. Within weeks of the arXiv posting, there were already 3 independent reanalysis papers attempting to reproduce or challenge the results. There were workshops being organised at major research institutions. Time on Webb was being requested urgently, a precious oversubscribed resource, specifically to conduct follow-up observations of K218b across as many wavelengths and as many transits as possible. The urgency has a specific edge to it that the DMS variability creates. If the signal were stable and robust, scientists could observe K218b on their own schedule, carefully, methodically. But if the signal is genuinely variable, if it rises and falls with biological rhythms or whatever other process is driving it, then there may be a time-sensitive component to the follow-up. Miss the next bloom, and you might not see the signal again for years. Observe during a quiet period and you might incorrectly conclude there's nothing there. This is a strange position for planetary science to find itself in. Usually we deal with planets on geological timescales, billions of years, features that have been there for eons and will be there long after we're gone. The idea that you might need to catch a planet at the right moment, that atmospheric chemistry might be varying fast enough to matter for your observation schedule, that's new. That's almost a live feeling in itself, and it raises a question that some researchers are beginning to ask openly. What do we do if we confirm this? What happens next? Chapter 7. What confirmation would mean? Let's imagine for a moment that all of this holds up, that the follow-up observations, the ones currently being planned and requested and argued over, confirm the DMS detection at 5 sigma or above, that the variability is confirmed as real and is demonstrated to be inconsistent with any non-biological process we can identify or model, that the full weight of the evidence assembles itself into something that the scientific community has to take seriously as a biosignature. What happens? The short answer is, we don't really know. We've never been here before, and the plans and protocols that exist for this scenario are surprisingly thin given how long we've been thinking about the question. There's a long tradition in the search for extraterrestrial intelligence, SETI, of protocols for what to do if you detect an artificial signal from another civilization. The basic framework, developed over decades, involves a verification process, a consultation with the international scientific community, and then a public announcement through established channels. The idea is to prevent premature disclosure, avoid panic, and ensure that what you're claiming to have found is actually what you think it is before you tell the world. But those SETI protocols were designed with a very specific scenario in mind. A radio or optical signal, clearly artificial, clearly originating from a technological civilization. The K218b situation is completely different. There's no signal in the communication sense. There's an atmospheric chemistry measurement, a detection of a molecule that might be biological in origin. The distinction matters enormously. A technological signal from another civilization is unambiguous in its implications. Intelligent life built that transmitter. But a biological atmospheric signature is far more ambiguous. Even if DMS in K218b's atmosphere is definitively confirmed as real and definitely of biological origin, what does that tell us? That some form of life exists there. Marine-type microorganisms, maybe. Something that produces DMS the way Earth's phytoplankton do. But we would know almost nothing about what that life actually is. We wouldn't know if it's simple or complex, single-celled or multicellular, still thriving or in its last gasps. We wouldn't be able to communicate with it or visit it. 124 light-years is so far that even if we sent a probe at the fastest speed any object humans have ever built has travelled, it would take over 1 million years to arrive. The discovery would be, in one sense, the most important thing humanity has ever learned, and in another sense, it would leave us completely unable to do anything about it in any direct way. The philosophical and cultural impact, though, that's a different story. The effect on how human civilization understands its place in the universe would be immediate and total. Every religion, every philosophy, every story we tell about what it means to be alive and aware in a universe of otherwise inert matter, all of it would need to be reconsidered in the light of the knowledge that life exists elsewhere, not just might exist, exists. Some researchers think the public is more prepared for this than it used to be. Decades of science fiction, of growing scientific literacy, of the Kepler and K2 missions demonstrating that planets are everywhere and life-friendly planets are common. All of this has laid a kind of cultural groundwork. Polls consistently show that a large majority of people in most countries already believe that life probably exists elsewhere in the universe. A confirmation might be, for many people, less a shock than a vindication. But belief is different from knowledge, and the difference between probably somewhere out there and, yes, right here, these specific molecules, this specific planet, 124 light-years away in Leo, that difference is not nothing, it's a chasm, and crossing it, even with tentative and incomplete evidence, changes something fundamental about the human experience. These are the thoughts that occupy planetary scientists at 3 a.m, staring at spectra on their laptop screens, wondering what they're looking at. Chapter 8. The cases for and against. Let's do something that good science demands. Let's steelman the opposition. Not everyone is convinced that the 2025 K2-18b paper represents anything more than an interesting but ultimately explicable measurement anomaly. There are serious scientists, credible scientists, scientists who have spent their careers thinking about biosignatures and atmospheric characterization, who look at the data and see something very different from what Madhusudan's team sees. Here are the strongest counter-arguments. The case for causal skepticism. First, DMS has many spectral features that overlap with those of other molecules. The infrared absorption spectrum of dimethyl sulfide is not entirely unique. Other sulfur-containing compounds, and even some combinations of more common atmospheric gases, can produce spectral features in the same wavelength ranges. When you're working at the edge of instrumental sensitivity, when the signal is weak and the noise is significant, there's a real risk of misidentifying what you're seeing. The 2025 team used sophisticated retrieval algorithms, statistical methods that find the best fit atmospheric composition to match the observed spectrum. But those algorithms are only as good as the models they're built on, and there's always a possibility that the model space doesn't include the true explanation. Second, the host star is a red dwarf. Red dwarfs are problematic for transmission spectroscopy in ways that are still being actively researched. They're covered in star spots, cooler, darker regions on the stellar surface, and they produce flares that can significantly alter the star's ultraviolet and infrared output. When a planet transits a red dwarf with star spots, the apparent spectrum of the planet's atmosphere can be contaminated by the spectrum of the unocculted star spots, the parts of the star's surface that aren't covered by the planet's disk during the transit. This stellar contamination effect can, in principle, mimic or mask genuine atmospheric features. The 2025 team corrects for this, but red dwarf stellar contamination is notoriously hard to fully characterize, and some researchers argue the corrections may be insufficient. Third, the variability of the DMS feature, rather than being a sign of biological activity, could simply be a sign that the detection isn't real. If you're measuring something near the noise floor, something right at the edge of what your instrument can detect, you expect it to appear and disappear and fluctuate not because the real signal is changing, but because you're measuring noise that happens to be correlated with a real signal some of the time. The apparent variability might be the strongest argument against the detection, not for it. The case for taking it seriously. On the other side, the advocates for taking this result seriously make equally compelling points. The DMS feature appears at the right wavelengths, not one wrong wavelength and not another. the specific pattern of absorption is consistent with DMS's known spectrum. Alternative explanations, other molecules that could produce similar features, have been tested against the data and do not fit as well. This doesn't prove it's DMS, but it means the DMS interpretation isn't simply the result of wishful thinking. The atmospheric context makes sense. Carbon dioxide plus methane in a hydrogen-rich atmosphere, combined with a potential DMS signal, this isn't a random collection of molecules. It's a combination that fits a coherent picture, a Hycean ocean world with an active biological component. The consistency of the overall atmospheric interpretation across multiple molecules is more persuasive than any single detection. And the variability, rather than undermining the case, actually provides an additional constraint that abiotic explanations struggle with. If it were noise, you'd expect the strength of the feature to vary randomly around some mean value. But if it tracks something real, if the epochs of stronger and weaker signal correspond to something systematic about the planet's orbit, its star's activity cycle, or some other physical parameter, that would be a genuinely new kind of evidence. Researchers are looking at this right now, trying to see if the epochs of stronger DMS signal correlate with anything. The orbital phase of the planet, the flaring rate of the star, the time of year relative to any periodic phenomenon in the system. It's painstaking work, but if a correlation emerges, it could be enormously revealing. This is where the science stands as of early 2025, deeply uncertain, actively contested, and moving fast. Chapter 9. The History of Almost. Before we go further into what's happening right now with K2-18b, we need to talk about history. Because science, real science, not the cleaned up version that gets presented in textbooks, is full of moments exactly like this one. Moments where the evidence pointed towards something extraordinary, where the data seemed to be whispering something world-changing, where researchers stood at the edge of a precipice and looked down into the unknown, and then sometimes the ground gave way, and sometimes it held. Understanding those previous moments, what they got right, what they got wrong, and why, is essential if you want to understand what's actually happening with K2-18b today. Because the history of the search for extraterrestrial life is not simply a history of failure. It's a history of learning how to ask better questions, build better tools, and resist both the temptation to overclaim and the equally dangerous temptation to dismiss things that deserve to be taken seriously. The most famous near miss in the history of astrobiology is probably the Allen Hills 84001 meteorite, OLH 84001. In August 1996, NASA held a press conference that was, at the time, one of the most watched scientific announcements in history. President Bill Clinton made a statement from the White House Rose Garden. The cover of Time magazine showed a close-up of the meteorite rock with the words, "Life on Mars." Scientists from NASA's Johnson Space Center had been studying a chunk of Martian rock that had been blasted off Mars by an asteroid impact roughly 15 million years ago, had traveled through space, and had fallen to Earth in Antarctica about 13,000 years ago. Inside the meteorite, they claimed to have found 4 lines of evidence that, taken together, were consistent with ancient microbial life. Polycyclic aromatic hydrocarbons, complex organic molecules associated with biological decay, carbonate globules that formed at low temperatures where life could exist, magnetite crystals with a shape and purity that, on Earth, are produced almost exclusively by certain bacteria, and tiny structures that looked, under electron microscopy, like fossilized nanobacteria, sausage-shaped forms roughly 100 nanometers long. The announcement was a sensation, and then, slowly, it unraveled. Over the following years, alternative explanations for each of the 4 lines of evidence were developed and validated. The PAHs were contamination from Antarctic ice meltwater, Earth organic molecules that had percolated into the meteorite after it landed. The carbonates probably formed at high temperatures incompatible with life. The magnetite crystals, on closer examination, were not as distinctive as initially claimed. Inorganic processes can produce similar morphologies, and the nanobacteria turned out to be far too small to contain the biochemical machinery necessary for life. Structures that size simply cannot be a cell in the way we understand cells to function. By the early 2000s, most scientists had concluded that ALH 84001 did not contain evidence of life. The original team pushed back, and some aspects of the debate continued for years, but the consensus shifted. The extraordinary claim had not survived the scrutiny that followed. What's the lesson? Not that scientists were stupid or negligent in 1996. The researchers who published the ALH 84001 analysis were serious, careful scientists doing serious, careful work. The lesson is about the structure of evidence. Any single line of evidence, no matter how provocative, is vulnerable to alternative explanations. Multiple independent lines of evidence that all point toward the same conclusion are much harder to explain away. And even multiple lines of evidence, when they're all explaining the same phenomenon in the same sample, can sometimes share a common systematic flaw that undermines them all at once. The error bars on one measurement might conceal a mistake that propagates invisibly through every downstream conclusion you draw. For K218b, this lesson cuts both ways. The combination of CO2, methane, and DMS, in an atmospheric context that makes chemical sense, is more persuasive than any one molecule alone. But all three detections come from the same type of measurement, transmission spectroscopy with Webb, and they share potential systematic errors related to stellar contamination and atmospheric modelling assumptions. An independent detection through a completely different measurement technique would be far more powerful. Unfortunately, for a planet 124 light-years away, we don't have that option available to us at the sensitivity we need. We have essentially one technique available: Webb's transmission spectroscopy. Accumulating more of the same type of evidence is valuable, but it doesn't provide the kind of independence that makes a case truly airtight in the eyes of the most rigorous skeptics. Then there is the phosphine affair. In September 2020, a team led by Jane Greaves of Cardiff University announced in the journal Nature Astronomy that they had detected phosphine, pH 3, in the atmosphere of Venus at concentrations of about 20 parts per billion. Like DMS, phosphine on Earth is produced primarily by biological processes, and there is no well-understood abiotic pathway that produces it in significant quantities under Venus-like conditions. The detection, if real, would be enormously significant, not because Venus is considered habitable today. It absolutely is not, with surface temperatures around 465 degrees Celsius and crushing atmospheric pressure. But because the upper cloud layers of Venus, where temperatures and pressures are more moderate, have been proposed as a potential niche where aerial microorganisms might survive. The phosphine detection generated headlines that looked almost exactly like today's K218b headlines. Possible sign of life detected in the atmosphere of Venus? The reaction from the scientific community was immediate and intense. Independent groups began reanalyzing the data from the James Clerk Maxwell Telescope and the ALMA observatory that Greaves' team had used. What followed was a protracted and sometimes acrimonious scientific dispute. Other teams found that the original data reduction contained errors that, when corrected, significantly reduced the apparent phosphine signal. There were debates about calibration, about the subtraction of interfering spectral lines from sulfur dioxide, about statistical methodology. Greaves and her collaborators responded to each criticism and maintained that the phosphine detection was real, though perhaps at lower concentrations than initially reported. The argument continues to this day, unresolved, with new observations planned and the scientific community genuinely split on who is right. The Venus phosphine affair is instructive for K218b for a different reason than ALH 84001. The Martian meteorite story is about the internal consistency of a set of evidence and the importance of alternative explanations. The Venus phosphine story is about data quality and the vicious difficulty of extracting weak signals from noisy data at the absolute edge of what current instruments can achieve. Both lessons apply directly to K218b. The DMS detection is right at that edge. The data quality issues are real, the alternative explanations are actively being explored, and the history suggests that the right response is neither to dismiss nor to celebrate, but to observe more carefully with more instruments, more often until the evidence assembles itself into something definitive, or until it quietly fades away into the background noise, leaving behind only the question of what it was that we briefly thought we saw. And there is one more historical episode that deserves mention here, because it resonates with the K218b story in a way that is almost eerie in its parallels. In 1967, Jocelyn Bell Burnell, a graduate student at Cambridge University, the same Cambridge where Madhusudhan now works, detected a radio signal from the sky that repeated with extraordinary precision. A pulse every 1.3373 seconds, unwavering, metronomic, impossibly regular. The signal was so perfectly timed that the team initially labelled it LGM1, Little Green Men 1. They were half joking, but only half. Because at that moment, sitting with data that no one had ever seen before with no established framework for what they were looking at, the possibility of an intelligent origin was not absurd. It was genuinely on the table. It turned out to be a pulsar, a rapidly rotating neutron star emitting a beam of radio waves that swept across the Earth like a cosmic lighthouse. Not life, not intelligence, but a new class of astronomical object that no one had known existed. The discovery earned a Nobel Prize, and for a brief, breathless period before the explanation arrived, the researchers who held that data handled it exactly the way all these researchers should handle their findings, with rigour, with skepticism, with careful verification, and with the willingness to consider the most extraordinary possibility while simultaneously working hardest to disprove it. That's the model, that's the template, and by and large the teams working on K2-18b are following it faithfully, even under the pressure of global media attention, competitive funding environments, and the weight of potentially the most important question in the history of science. Chapter 10. The Machinery of Webb. To really understand why this moment matters, why the K2-18b observations are qualitatively different from earlier suggestive results in the search for biosignatures, you need to understand what James Webb is actually doing, mechanically and technically, when it observes a planet like K2-18b. Because Webb isn't just a bigger Hubble, it's a fundamentally different kind of instrument, and the things it can do that no previous telescope could do are precisely what make these observations possible in ways that would have been unimaginable to the generation of astronomers who first identified K2-18b as an interesting target. Webb is a 6.5 metre primary mirror telescope, compared to Hubble's 2.4 metres. That difference in collecting area, Webb has roughly 7 times the light-gathering area of Hubble, matters enormously for faint signal detection. But the mirror size is almost secondary to Webb's real superpower, which is its wavelength coverage and the extraordinary sensitivity it achieves in the infrared. Hubble operates primarily in ultraviolet and visible light, with some near-infrared capability. Webb operates almost entirely in infrared, from about 0.6 micrometers at the very edge of visible red light, all the way out to 28 micrometers in the mid-infrared. This is the wavelength range where molecules speak, where atoms vibrating within molecular bonds, carbon bonded to oxygen, sulfur bonded to carbon, nitrogen bonded to hydrogen, absorb and emit photons in patterns that are as unique and identifying as a fingerprint. This is where the chemistry of a planetary atmosphere reveals itself, if you have a telescope sensitive enough to listen. For transmission spectroscopy, the technique Webb uses to decode exoplanet atmospheres, the setup is elegant in concept and diabolical in execution. You wait for the planet to pass in front of its star. During the transit, the planet's opaque disk blocks some fraction of the star's light, but around the edges of that disk, starlight filters through the planet's atmosphere. Molecules in the atmosphere absorb specific wavelengths of the infrared light as it passes through. When you measure the spectrum of the star with the planet transiting versus the spectrum without the planet transiting, the difference, the residual, tells you which wavelengths were selectively absorbed by the atmosphere. And because every molecule absorbs at its own characteristic set of wavelengths, that residual spectrum is effectively a list of ingredients. A chemical inventory of the atmosphere of another world, conducted across 124 light-years of empty space, using nothing but light. It sounds straightforward. In practice, it is a measurement of almost supernatural difficulty. The depth of the transit, the fraction of starlight blocked by K2-18b's opaque disk, is about 2.6%. That's the total whole planet signal. The atmospheric transmission signal, the additional dimming caused by the atmosphere at specific wavelengths, is orders of magnitude smaller. We're talking about detecting a change of a few parts per 10,000 or fewer in the brightness of a star over 100 light-years away, caused by a thin shell of gas around a planet smaller than Neptune. To put that in human terms, imagine standing a kilometre away from a light bulb and trying to detect the tiny change in brightness caused by a piece of tissue paper passing in front of one edge of the glass. Now imagine doing that from across a continent. To extract that signal, Webb stares at K218b for the entire duration of each transit, roughly 3 hours, plus significant time before and after to establish baseline brightness levels, collecting photons continuously and without interruption. The raw data is then run through multiple stages of processing. Instrumental systematics, tiny electronic drifts and detector artifacts that are inherent to any physical instrument, must be removed. Stellar variability, the natural flickering and pulsing of the host star itself, must be corrected for. The in-transit spectrum is divided by the out-of-transit spectrum to isolate the planetary atmospheric contribution, and then the residual spectrum is fed into atmospheric retrieval algorithms, sophisticated statistical codes that search through a vast model space to find the atmospheric composition that best explains the observed absorption pattern. These retrieval algorithms are themselves impressive achievements of scientific software engineering. They typically use Bayesian inference frameworks, mathematical approaches that combine the data with prior knowledge about what atmospheres are likely to look like, and that produce not just a best-fit answer, but a full probability distribution over all possible atmospheric compositions. They tell you not only the best fit has this much CO2, but there's a 95% probability that CO2 is between these two concentration values. The width of that probability distribution tells you how confident you can be. For carbon dioxide and methane in K218b's atmosphere, the retrieval probability distributions are relatively narrow and clearly peaked at non-zero concentrations. Those detections are robust. For DMS, the distribution is broader, more uncertain, but the peak is clearly away from zero. The data prefer some DMS to no DMS, even if they can't pin down the concentration precisely. Webb has 4 scientific instruments, and the K2-18b observations have used several of them. NIRIS, the near-infrared imager and slitless spectrograph, covers wavelengths from about 0.6 to 2.8 micrometers. NIRSpec, the near-infrared spectrograph, extends from about 0.6 to 5.3 micrometers, with exceptional sensitivity across its range. These two instruments together cover the wavelength range where the key absorption features of CO2, CH4 and DMS are most prominent, and they formed the core of the initial observing program. More recently, MIRI, the mid-infrared instrument, has entered the picture. MIRI covers wavelengths from 5 to 28 micrometers, a regime that opens up entirely new windows into atmospheric chemistry. At these longer wavelengths, molecules have additional absorption features, sometimes stronger ones, that are completely independent of the near-infrared features already detected. Carbon dioxide has a major absorption band near 15 micrometers. Methane has features near 7.7 micrometers, and DMS, critically, has mid-infrared absorption features that are spectrally distinct from those in the near-infrared, and that would provide genuinely independent confirmation of the near-infrared tentative detection. The MIRI data from K218b's late 2024 observations is being analysed as of early 2025, and its release is one of the most anticipated events in the recent history of planetary science. If MIRI sees DMS features at wavelengths consistent with the near-infrared detection, and at concentrations that agree with the retrieval results, the statistical case for DMS in K218b's atmosphere will improve dramatically. If MIRI does not see the expected DMS features, if the mid-infrared spectrum is inconsistent with the near-infrared DMS interpretation, then the near-infrared detection needs to be seriously reconsidered. The sensitivity of Webb was always expected to transform exoplanet atmospheric science. But the K218b results have demonstrated something even Webb's designers were not fully certain about in advance, that the telescope is sensitive enough to detect trace molecules, molecules present at the parts per million level, in the atmosphere of a sub-Neptune planet over 100 light-years away. That capability places us in a completely different regime of planetary science, not just better than what came before, but categorically new. We are, for the first time, doing remote chemistry on alien worlds, reading the molecular inventory of planetary atmospheres across distances that no human being will ever physically cross, and doing it well enough that the results are scientifically meaningful, not just suggestive hints, but actual spectroscopic data with real statistical power. That's extraordinary. And it comes with a commensurate responsibility to be rigorous, careful and honest about what the measurements do and do not actually tell us, because Webb is powerful enough to find things that are genuinely there. and occasionally powerful enough to be misled by things that look real but aren't. The boundary between those two outcomes is exactly where the science of K218b currently lives, and the work of the next year will be about determining, as definitively as current technology allows, which side of that boundary the DMS signal falls on. Chapter 11. What lives in a hydrogen ocean? Let's go somewhere strange for a moment. Let's leave behind the telescopes and the spectral retrieval codes and the peer-reviewed papers, and try to actually imagine being on K218b. To the extent that imagination can stretch across 124 light-years and encompass conditions that have no parallel in any human experience, let's try to picture what this world is actually like. Because the abstract language of science, sub-Neptune, hydrogen-rich atmosphere, Hycean ocean world, tends to drain the colour from what is, if the Hycean hypothesis is correct, one of the most alien and astonishing environments in the observable universe. K218b orbits a red dwarf star. Red dwarfs are the most common type of star in the galaxy. Roughly 70% of all stars are red dwarfs, and yet our own Sun is not one of them, which means we have no intuitive sense of what it's like to be bathed in red dwarf starlight. The star K2-18 emits far less total light than our Sun, and what light it does emit is skewed heavily toward the red and near-infrared end of the spectrum. The quality of illumination it provides is fundamentally different from what we're used to. Dimmer, redder, with far less of the blue wavelengths that scatter through our atmosphere to give Earth its characteristic blue sky. If you could somehow be suspended in K218b's upper atmosphere, which you could not because the atmospheric composition would be instantly lethal and the pressure would be catastrophic, the star overhead would appear reddish-orange, perhaps slightly larger in angular diameter than our Sun appears from Earth, because the planet orbits closer to its cooler, smaller star. The sky around the star might glow with strange colours, the product of different scattering physics in a hydrogen-dominated atmosphere, rather than Earth's nitrogen-oxygen mix. Hydrogen scatters light differently. The visual experience would be alien in ways that are difficult to fully articulate, but that would be immediately and viscerally apparent. As you descended from the upper atmosphere into the lower layers, pressure and temperature would both increase. The atmosphere would thicken and grow denser around you. At some depth, you would begin to encounter water vapour, enormous quantities of it, because below you, the ocean that defines this world is vast and warm and constantly evaporating into the atmospheric column above it. The humidity at the base of the atmosphere, just above the ocean surface, would be extreme. The transition from gas to liquid ocean might not be a sharp boundary. At the temperatures and pressures expected near the ocean surface of a Hycean world, water can exist in states that blur the distinction between gas and liquid, supercritical or near supercritical states where the properties of the fluid grade continuously between phases, rather than switching abruptly at a defined surface. The ocean itself is the defining feature of the world, potentially thousands of kilometers deep, so deep that the very concept of a seafloor in any meaningful sense becomes questionable. At extreme depths, the pressure would be so crushing that water transitions to exotic high-pressure ice phases, dense, crystalline forms of water that exist only at pressures found nowhere in Earth's oceans, forms with names like Ice 6 and Ice 7 that are produced in diamond anvil cell experiments in terrestrial laboratories, and that behave in ways that still puzzle materials scientists. Whether these deep ice phases provide any kind of floor that interfaces with rocky mantle material, and whether that interface could generate the chemical gradients and mineral nutrients that are thought to be important for the origin and sustenance of life. These are genuinely open questions. Life, if it exists in the Hycean ocean of K218b, almost certainly does not exist throughout the entire depth of that ocean. The conditions at the base are almost certainly incompatible with biology as we understand it. Too much pressure, too little access to chemical energy sources, too isolated from the photon flux from the star above. If life is there, it's probably at or near the ocean surface, in the zone where light from the star penetrates, and where the chemical interface between the atmosphere and ocean creates the kinds of gradients and energy sources that biology can exploit. And this is where the DMS story becomes coherent. On Earth, dimethyl sulfide is produced by marine phytoplankton, microscopic photosynthetic organisms that live in the sunlit surface layer of the ocean, the photic zone, where light penetrates sufficiently for photosynthesis. The phytoplankton produce a compound called dimethylsulfonopropionate, or DMSP, as part of their cellular chemistry. It functions as an osmolyte, helping regulate the cell's internal salt concentration. When phytoplankton are grazed by zooplankton, or when they die and are broken down by bacteria, the DMSP is converted to DMS. DMS is volatile. It evaporates readily and bubbles up from the ocean surface into the atmosphere, where it participates in cloud formation chemistry and eventually gets destroyed by photochemical reactions. If there are organisms in K2-18b's ocean that produce DMS or DMS-like compounds through analogous metabolic pathways, if the Haitian Ocean has something playing the ecological role of Earth's phytoplankton, you would expect that DMS to bubble up through the ocean's surface and accumulate in the hydrogen atmosphere above, exactly as it does on Earth. The fact that a DMS consistent spectral feature appears in Webb's observations of K2-18b in an atmospheric context that is otherwise consistent with the Haitian world model fits this picture with remarkable coherence. But we need to be careful about letting that coherence seduce us into overconfidence. Coherence is not proof. A story can be internally consistent and still be wrong. What the coherence does is tell us that the biological interpretation is not absurd, not a desperate reach, not a misidentification of an unrelated phenomenon. It's a legitimate scientific hypothesis that is currently consistent with the available data. That's meaningful. That's actually quite significant, given how high the bar for legitimate scientific hypothesis is in this field. But it's the beginning of a case, not the end of one. The radiation environment on K2-18b deserves specific mention because it's one of the most important and most often overlooked aspects of the habitability question for Haitian worlds. Red dwarf stars are not gentle hosts. They are magnetically active, producing stellar flares, sudden, violent releases of electromagnetic energy, at rates far exceeding anything our own sun generates. The flares pump out intense ultraviolet and X-ray radiation that bombards the planet's atmosphere. For life at or near the ocean surface of a Haitian world, this radiation is a major challenge. Ultraviolet light destroys complex organic molecules. It damages cellular structures. It drives the photochemical reactions that can break down biosignature gases like DMS before they can accumulate to detectable concentrations. But the very thickness of the hydrogen atmosphere that makes Haitian worlds so alien might also provide crucial protection. A deep hydrogen atmosphere absorbs and scatters ultraviolet radiation, reducing the flux that reaches the ocean surface. The ocean itself provides additional attenuation with depth. Life at a few meters depth in a Haitian ocean might be substantially shielded from stellar radiation. And the microorganisms in Earth's most radiation-exposed environments, the surface layers of the open ocean, the ice sheets of Antarctica, the bare rock faces of mountains at high altitude, have evolved a remarkable array of UV protective pigments, repair mechanisms, and behavioral strategies for minimizing radiation damage. There is no reason in principle why Haitian world life could not evolve similar adaptations. Wherever we have looked on Earth with sufficient care, we have found life operating in conditions that would once have seemed impossible. In hydrothermal vents at the ocean floor where temperatures exceed 400 degrees Celsius, in hypersaline brine pools where most biochemistry should grind to a halt, in solid rock kilometers underground, sustained by chemical reactions between minerals and water, in the cooling water of nuclear reactors, in clouds of sulfuric acid, in the hyperdry soils of the driest deserts on Earth. Life is extraordinarily adaptable. The biochemistry that underlies it is extraordinarily flexible, and the range of environments in which carbon-based chemistry can organize itself into self-replicating, energy-harvesting, entropy-resisting systems is far wider than our intuitions, evolved in the comfortable conditions of Earth's surface, tend to suggest. Chapter 12, The Other Explanations, we've already discussed some of the skeptical arguments about the DMS detection itself, instrumental effects, stellar contamination, modelling assumptions, but there's a second layer of skepticism that deserves its own careful attention. Even if DMS is genuinely present in K2-18b's atmosphere, does that actually prove there's life, or even strongly suggest it? This question is more complicated than it might appear, and the answer is currently somewhere between not definitively and more than any other explanation we currently have. Let me explain why it's that complicated. The assumption that DMS is exclusively biological in origin is based entirely on our experience with Earth. On Earth, we have not found a significant abiotic source of DMS, but Earth is one planet with one chemistry operating in one set of geological and photochemical conditions over one planetary history. The universe contains an incomprehensible range of chemical environments, and it is not just possible but genuinely scientifically plausible that abiotic pathways for DMS production exist in environments that simply don't occur on Earth. Environments that K218b might have in abundance. For example, some laboratory experiments have shown that organic sulfur chemistry in reducing hydrogen-rich environments can produce sulfur-containing organic compounds, including some that structurally resemble DMS. The reaction yields in these experiments are low relative to what biological production achieves on Earth, but extrapolated to the enormous volume and timescale of a planetary atmosphere, even small abiotic production rates might accumulate to detectable concentrations. This research is preliminary, with large uncertainties, but it represents exactly the kind of work that needs to be done before DMS can be firmly categorized as a biosignature in all planetary environments rather than just on Earth-like worlds. There's also the question of spectral confusion, whether what looks like DMS in K218b's spectrum might actually be another molecule with overlapping absorption features. The infrared spectrum of dimethyl sulfide is not entirely unique. Other sulfur-containing organic compounds, and even some combinations of simpler molecules, produce spectral features in similar wavelength ranges. Atmospheric retrieval algorithms test multiple candidate molecules and compare how well each fits the data, but they can only test molecules that are included in their model libraries. If the true absorber is a molecule that researchers haven't thought to include, perhaps an exotic sulfur compound that forms in high-pressure hydrogen-water environments and isn't well characterized in laboratory spectral databases, the algorithm might misidentify it as DMS simply because DMS is the closest match in the library it has available. This is not a hypothetical concern. Atmospheric spectroscopy has been fooled by molecular misidentification before. The history of the Venus phosphine detection includes exactly this issue. Debates about whether the observed absorption features were phosphine or sulfur dioxide or some combination of both. The spectral databases for many molecules, especially complex organics and unusual inorganic compounds, are incomplete. Molecules that are rare or exotic on Earth may not be well characterized in the laboratory databases that inform atmospheric modeling, even though they might be common on worlds with different chemistries. The variability of the DMS signal introduces yet another complicating factor in the interpretation. We noted in Part 1 that the apparent fluctuation in the DMS feature strength could be interpreted either as evidence of biological activity, blooms and diebacks analogous to phytoplankton dynamics, or as evidence that the detection isn't robust, that what looks like variability is just noise varying above and below the detection threshold. But there's a third interpretation that deserves consideration. Atmospheric chemistry itself can produce time-variable features under certain conditions. If the production rate of a molecule is steady but its destruction rate varies, perhaps because the stellar flare rate from K218 is variable, driving photochemical DMS destruction at varying rates, you could get a variable atmospheric concentration without any biological fluctuation. If DMS is being produced abiotically at a constant rate but destroyed by UV-driven photochemistry, at a rate that tracks the star's activity cycle, the observed atmospheric DMS concentration could oscillate in phase with the star's magnetic activity cycle. This would produce exactly the kind of variability seen in the observations, without any biology at all. Testing this specific hypothesis requires better characterization of K218's stellar activity. How often does it flare? How does its flare rate vary over time? Is there a measurable activity cycle, analogous to the Sun's 11-year sunspot cycle, that could impose periodic variations on atmospheric photochemistry? These are questions that can be addressed with existing ground-based telescopes and with archival data from missions like TESS, which has been monitoring K218's brightness variability for years. Several groups are working on exactly this analysis right now, and its results will be crucial for interpreting the DMS variability. The honest summary of where the other explanations analysis stands is this. The biological interpretation of the K2-18 BDMS detection is consistent with the data, coherent with the broader atmospheric picture, and not obviously contradicted by any known physical or chemical process. But the abiotic alternatives, misidentification, low-level abiotic production, stellar activity-driven photochemical variability, are also not ruled out. They're less elegant, less coherent with the full picture, and in some cases require invoking processes that we don't currently have evidence for on K218b. But less elegant is not the same as wrong. Science has no aesthetic standard. The universe is not obligated to be elegant. It's obligated only to be consistent with the evidence. And that's where more and better evidence comes in. Chapter 13. The People in the Room. There's a human story here that often gets lost in the technical details, and it deserves to be told carefully, because the scientists who are working on K218b are not abstractions. They are real human beings with careers and families and professional reputations and personal histories that shaped why they chose to spend their working lives doing this particular thing. Understanding something about who they are and what drives them illuminates why this moment feels the way it does, both within the community and from the outside looking in. Nikku Madhusudan is, by all accounts, one of the most respected theoretical astrophysicists of his generation. His work on exoplanet atmospheres spans more than a decade and includes some of the foundational papers on atmospheric retrieval methodology and the theoretical composition of different planetary types. The Ocean world concept he developed before Webb launched was not a publicity stunt or a media grab. It was a serious theoretical prediction, grounded in planetary physics, that was already being discussed in the academic community long before the observations came in. He's not someone who has made a career of overblown claims. His scientific record is one of careful, methodical work that advances the field through rigorous theory and equally rigorous data analysis. When the 2023 paper came out, Madhusudan was conspicuously careful in every interview and public statement. He repeatedly cautioned against concluding that life had been found. He emphasized the tentative nature of the DMS detection. He called for precisely the kind of follow-up observations that the community has since been scrambling to conduct. That combination, genuinely exciting results, presented with genuine scientific humility, is a significant part of why the broader community has engaged seriously with the work, rather than dismissing it as overreach. But there's a broader human dimension to this story that extends well beyond any single researcher. The teams working on K218b span multiple countries, multiple institutions, and multiple generations of scientists. There are senior researchers who have spent their entire careers building toward the capability that Webb represents, who have written the theory, designed the techniques, trained the students, and waited for decades for a telescope powerful enough to actually use them. For those people, this moment is the culmination of a professional lifetime. The weight of that is not easy to carry lightly, especially when the result is ambiguous and the pressure to interpret it definitively is intense, and there are young researchers, graduate students and postdoctoral fellows, for whom K218b is the defining project of their early scientific lives. The pressure on them is of a different kind. The pressure of establishing a reputation in a field where the highest stakes question in the history of science is being actively contested, where every preprint generates immediate global media attention, and where being wrong in a very public way can shape a career for years. Science is supposed to be about the pursuit of truth, not about career management, and most scientists, especially young ones, genuinely believe that and genuinely try to practice it. But the structural incentives of academic science, publication metrics, grant success, institutional prestige, create pressures that don't always align perfectly with pure epistemic virtue. The communication challenge these researchers face is genuinely difficult. How do you convey appropriate excitement about a result that might be the most important discovery in human history, without triggering the kind of runaway media hype that distorts public understanding and ultimately damages the credibility of science itself? The ALH 84001 experience is a cautionary tale that everyone in astrobiology knows intimately. The damage done to the field by the subsequent retraction, not of the paper itself but of the public confidence that had been invested in its claims, took years to repair. Nobody wants to be responsible for a repeat of that episode, especially not at this scale, with this question, with this level of global attention. What's notable about how the K218b results have been communicated is that, For the most part, the researchers have navigated this tension successfully. The papers are carefully hedged without being dishonest. The public statements are honest about uncertainty without being dismissive of what the data shows. The gap between "this is what we found" and "this is what it means" has been preserved and respected, even under enormous pressure to collapse it into a simpler, more exciting narrative. That epistemic discipline is itself a kind of scientific achievement, and it's one of the reasons why the K218b story, whatever it ultimately turns out to be, is already a landmark in the history of how science communicates with the public about questions of the deepest possible significance. Chapter 14. The next 6 months. So, where does all of this go from here? What are the concrete steps, the specific observations, the analyses and results that will shape the K218b story over the coming months and years? Because this is not a story that will be resolved by one more paper or one more observation. It's a story that will unfold gradually, through the accumulation of evidence that slowly and perhaps never quite completely tips the scale from intriguing possibility towards something more definitive. The most immediately anticipated result is the analysis of the MIRI mid-infrared observations from late 2024. These observations, covering wavelengths from 5 to 28 micrometers, represent a genuinely independent window into K218b's atmospheric chemistry. The CO2 and methane features detected in the near-infrared should appear again at mid-infrared wavelengths, verifying those detections independently and at different systematic errors than the original near-infrared analysis. The DMS mid-infrared features, if DMS is real, should also be present at wavelengths and strengths consistent with the near-infrared tentative detection. The MIRI analysis is technically challenging. The mid-infrared presents different instrument systematics and stellar contamination issues than the near-infrared, but several groups are working on it simultaneously, and cross-checks between independent analyses will help separate real atmospheric signals from instrumental artifacts. Additional Webb transit observations of K218b have been proposed and are under review by the telescope's Time Allocation Committee. These observations are specifically designed to test the variability of the DMS feature, to determine whether the signal fluctuations identified in the 2025 paper follow any systematic pattern that could help discriminate between biological and non-biological origins. The proposals request observations spaced to sample different phases of K218 stellar activity cycle, different orbital configurations and different seasons, to the extent that seasons is even a meaningful concept for a tidally influenced planet orbiting a red dwarf. Laboratory astrochemistry is ramping up in parallel. Experiments designed to test DM's production pathways in Hisian-relevant conditions, high-pressure hydrogen-water mixtures with dissolved sulfur compounds, irradiated by simulated red dwarf ultraviolet spectra, are being designed and implemented at several institutions. The results of these experiments will directly constrain the abiotic production rate of DMS under K2-18b-like conditions. If the experiments show that abiotic DMS production is negligible in these environments, the biological interpretation strengthens. If they show significant abiotic production, the interpretation becomes more complicated. Stellar characterization work is also underway. Better understanding of K218's flare rate, activity cycle, and spot coverage will enable more accurate corrections for stellar contamination in the transmission spectra. Ground-based monitoring campaigns using high-precision photometry and spectroscopy are tracking the star's variability in detail, building a dataset that will eventually allow atmospheric modelers to apply more accurate stellar corrections to the Webb data retrospectively as well as prospectively. All of this work is happening simultaneously, driven by teams on multiple continents who are collaborating, competing, cross-checking, and pushing each other toward better science. The pace is unusual, the stakes are clear to everyone involved, and within the next 12 months we will almost certainly know considerably more than we know now. Whether the DMS detection strengthens or weakens, whether the variability is real or illusory, whether the mid-infrared data confirms or contradicts the near-infrared picture. What we won't know even then is whether we're looking at life. That conclusion, if it ever comes, will require a weight of evidence that we are still building toward. Each observation, each experiment, each independent analysis is a brick in a structure whose final shape we cannot yet see. The structure might turn out to be a monument to the discovery of a life beyond Earth. or it might turn out to be a very thorough and scientifically valuable investigation of interesting, but ultimately abiotic atmospheric chemistry. Either way, we are learning. Either way, science is doing exactly what science is supposed to do, pressing its instruments and its minds against the hardest questions, refusing to accept comfortable ignorance, and following the evidence wherever it leads, even when it leads somewhere that makes us profoundly uncertain, even when the signal appears and then seems to vanish, and then beckons again from just beyond the edge of what we can see. Chapter 15. The Fermi Paradox gets complicated. There is a question that has haunted physics and astronomy for more than 70 years, a question so simple that a child can ask it, and so deep that the greatest minds of the last century have spent careers attempting to answer it without success. The question was posed, according to legend, over lunch at Los Alamos National Laboratory in the summer of 1950 by Enrico Fermi, one of the architects of the atomic age, a physicist of almost supernatural intuitive power, who looked up from his meal and asked his colleagues, with characteristic directness, "Where is everybody?" The logic behind the question is straightforward. The universe is approximately 13.8 billion years old. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. A significant fraction of those stars host planets. A significant fraction of those planets are in their star's habitable zone. If life arises wherever conditions allow it, if it is a natural consequence of chemistry given the right environment and enough time, then the universe should be teeming with it. And if even a tiny fraction of that life eventually develops intelligence and technology, then technological civilizations should have had billions of years to expand, communicate, and make their presence known across the galaxy. And yet, silence. No alien radio signals, no megastructures, no visitors, nothing but an empty, quiet cosmos that gives no outward sign of containing anything except stars, gas, dust, and the cold mathematics of physics. This is the Fermi Paradox, and for 70 years proposed solutions have ranged from the sobering, maybe intelligent life is extraordinarily rare, maybe civilizations always destroy themselves before they can spread, to the deeply unsettling, maybe they're there but we can't see them, maybe they're choosing not to communicate, maybe the universe contains something we don't understand that prevents the rise of technology on any world but ours, the possible detection of life on K2-18b, even microbial life, even simple ocean-dwelling microorganisms producing dimethyl sulfide, does not solve the Fermi Paradox, but it transforms it. Here's why. The Fermi Paradox only has teeth if life is common. If life arises readily, on many worlds, in many environments, then the silence of the cosmos becomes genuinely strange and demands explanation. If life is rare, vanishingly, cosmically rare, then the silence is simply what you'd expect. An empty cosmos tells you nothing particularly disturbing if life was always going to be sparse. The Drake equation, developed by astronomer Frank Drake in 1961 as a framework for estimating the number of communicating civilizations in the galaxy, contains a term called FL, the fraction of habitable planets where life actually arises. This is the term about which we have historically known essentially nothing. We have exactly one data point, Earth, and one data point is not a statistic. It tells you that life arose here in these conditions with this chemistry once. It tells you nothing reliable about how often that happens in general. A confirmed detection of life on K2-18b, a world with a completely different star, a completely different atmospheric composition, a completely different type of ocean at a completely different stage in its own planetary history, would give us a second data point. And in statistics, the difference between one data point and two data points is not simply a factor of 2. It is the difference between having no statistical power whatsoever and having the first glimmer of a genuine distribution. 2 points don't tell you everything, but they tell you something. Specifically, they tell you that life is not unique to Earth-like planets in Sun-like solar systems. They tell you that life can arise in at least 2 very different environments, which implies that the range of environments where life is possible is broader than a single example allows us to estimate. And if life arises in at least 2 very different planetary contexts, the statistical implication, however rough and preliminary, is that FL is not astronomically small, that life is not a 1 in a billion accident that occurred exactly once in the observable universe, that the conditions for life are replicated in enough places frequently enough that two examples are accessible to a species that has been doing planetary science seriously for only a few decades. That implication, if it holds up, makes the Fermi Paradox more acute, not less. Because if life is common, if it arises in hydrogen oceans as well as nitrogen-oxygen-covered rocky planets, then intelligent life should also be more common than previously feared, and the silence becomes more puzzling, not less. Unless intelligent life is the rare thing, unless microbial life is everywhere, in the hydrogen oceans of Hycean worlds, in the briny subsurface aquifers of icy moons, in the clouds of gas giants, in environments we haven't even thought to look. But the step from microbial to complex to intelligent life is the true rarity. The great filter might not be the origin of life at all. It might be the evolution of intelligence, or the development of technology, or the survival of technological civilizations past the point where their own power exceeds their wisdom. These thoughts are not peripheral to the K2-18b story, they're central to it, because what the K2-18b observations are potentially telling us is not just something about one planet. They're potentially telling us something about the distribution of life in the universe, about how common the first step is, about where we should focus our attention in the next century of planetary exploration, about what the silence of the cosmos, if it persists even after we've confirmed that life exists on K2-18b, actually means. If life is common and intelligence is rare, we are more alone in a meaningful sense than we feared even in our worst cosmological nightmares. Surrounded by living worlds, none of which ever grew sophisticated enough to notice us or to be noticed. A universe full of silent oceans and floating microorganisms, with no one to wonder about any of it except us. That possibility is both magnificent and crushingly melancholy, and it is directly on the table if the K2-18b observations hold up. Chapter 16. The Signal in Context. Let's step back from the philosophical implications for a moment and look at the K2-18b observation in the context of the broader exoplanet science program that Webb is conducting. Because K2-18b is not the only planet Webb is studying for atmospheric biosignatures. It's the most prominent, the one with the most provocative results, the one driving the most urgent follow-up. But it exists within a larger scientific effort that is transforming our understanding of planetary atmospheres across the galaxy. Webb is currently observing, or has observed, dozens of exoplanets in transmission spectroscopy mode. Most of these observations are not searching for biosignatures directly. They're aimed at characterizing the atmospheric compositions of hot Jupiters, warm Neptunes, and other planets that are not considered habitable, but whose large atmospheric signals make them useful testbeds for developing and validating the techniques needed to eventually study smaller, more habitable worlds. Every observation of a hot Jupiter's water vapor and carbon dioxide detection improves the retrieval algorithms. Every analysis of a mini Neptune's hydrogen envelope refines the atmospheric models. Every calibration of stellar contamination effects in red dwarf transits makes the K2-18b analysis more reliable. In this sense, K2-18b is the tip of an iceberg, the result of a decades-long investment in methodology, technology, and scientific infrastructure that has been building toward precisely this kind of observation. The broader Webb exoplanet program provides context, calibration, and comparative data that the K2-18b analysis depends on in ways that are not always visible in individual papers, but that are fundamental to the reliability of the conclusions. Other planets of the sub-Neptune and super-Earth type are being observed by Webb, and some of them are generating results that are relevant to the K2-18b story in important ways. The TRAPPIST-1 system, 7 Earth-sized planets orbiting an ultra-cool red dwarf about 40 light-years away, has been extensively observed with Webb. The inner planets of the TRAPPIST-1 system are too close to their star to be habitable, and Webb's observations have already confirmed that at least 2 of them, TRAPPIST-1b and TRAPPIST-1c, have little to no substantial atmosphere. This is important context. It tells us that not all planets around red dwarfs retain their atmospheres, and that atmospheric retention requires specific conditions of planetary mass, composition, orbital history, and stellar environment. K2-18b's retention of a substantial hydrogen-rich atmosphere, despite orbiting a red dwarf, suggests that it formed under conditions favourable for atmosphere retention, perhaps accreting enough volatile material in the outer regions of its protoplanetary disk, or perhaps protected from the worst of its star's early flaring activity by a magnetic field or by the sheer mass of its original volatile inventory. Understanding why K218b retained its atmosphere while the inner TRAPPIST-1 planets did not informs our models of which Hycean world candidates in the galaxy are worth prioritizing for future observations. There are several other sub-Neptune planets on Webb's observing list that, like K218b, orbit in their star's habitable zone and have size and mass parameters consistent with the Hycean world hypothesis. Planets like LHS 1140b, a super-Earth about 48 light-years away that some models suggest could be a Hycean world, are being observed with increasing urgency now that the K218b results have focused attention on this class of planet. If multiple Hycean world candidates show similar atmospheric chemistry to K218b, similar combinations of CO2, methane, and DMS-like features, that statistical pattern would be vastly more powerful evidence for biology than a single detection on a single planet. Conversely, if LHS 1140b and similar planets show completely different atmospheric chemistry, no DMS, different CO2 and methane ratios, a chemical context inconsistent with the Hycean model, that would also be informative. It would suggest that K218b's atmospheric chemistry is unusual, which could cut either way. It might mean that K218b is exceptionally biologically productive, or it might mean that its chemistry has an unusual abiotic driver that makes it anomalous among Hycean worlds rather than representative of them. The comparative planetology that Webb is enabling, the ability to characterize the atmospheric chemistry of many planets across a range of types and environments, is ultimately what will transform the K218b observation from an interesting anomaly into a scientifically meaningful statement about the distribution of chemistry and potentially biology in the galaxy. Individual detections, no matter how compelling, are limited by the possibility that they're unique to a particular set of conditions. Statistical patterns across multiple planets are the foundation of genuine scientific understanding. This is the longer game that Webb is playing, and K2-18b is its most dramatic opening move. Chapter 17. What we don't know about life itself. Here is something that doesn't get said often enough in discussions about the search for extraterrestrial life, and that needs to be said clearly before we can fully appreciate what a detection of DMS on K218b would or wouldn't mean. We do not know how life began on Earth. This is not a small gap in our knowledge. This is the central mystery of biology, the foundational question that every theory about extraterrestrial life ultimately depends on, and we genuinely, honestly, in 2025 do not have a verified scientific explanation for how the first self-replicating molecular systems arose from non-living chemistry on the early Earth. We have hypotheses, several compelling ones. The RNA world hypothesis proposes that early life was based on RNA molecules, which can both carry genetic information and catalyze chemical reactions, and that DNA and proteins came later, as more efficient specializations of functions that RNA originally performed alone. Hydrothermal vent hypotheses propose that the chemical gradients between superheated vent water and cold ocean water provided both the energy and the mineral surfaces needed to drive the formation of the first metabolic cycles, and eventually the first cells. Tidal pool hypotheses, championed by Charles Darwin himself in a famous letter about a warm little pond, propose that the cycling of wetting and drying concentrated organic molecules and drove the polymerization reactions needed to form long chains of nucleotides. Each of these hypotheses has supporting evidence and significant open questions. None of them has been definitively confirmed. The origin of life remains, as the Nobel laureate Jack Szostak has described it, one of the most important unsolved problems in science. Why does this matter for K218b? Because if we don't know how life begins, we can't calculate FL, the probability that life arises on any given habitable planet. And if we can't calculate FL, every statement we make about how common life should be in the universe is built on a foundation of ignorance rather than knowledge. This cuts in both directions. If the origin of life is extraordinarily improbable, if it required some specific sequence of chemical accidents that is so unlikely that it would almost never happen twice in the lifetime of the universe, then even the existence of habitable planets everywhere tells us nothing about whether life is common. Earth might be the sole exception, the universe's single successful experiment, the result of a cosmic lottery that almost certainly won't be repeated anywhere within our horizon. But if the origin of life is highly probable, if it is, as some researchers argue, essentially an inevitable consequence of chemistry given liquid water, organic molecules, and an energy source, then the universe should be full of life, and the existence of Hycean worlds and other habitable environments multiplies that expectation enormously. A confirmed detection of life on K2-18b would not tell us which of these scenarios is correct. 2 data points don't establish a distribution, but they do provide, for the first time, an empirical constraint on FL that is not derived from theory or philosophy, but from observation. They would tell us that in the relatively small sample of worlds that Webb has been able to examine in atmospheric detail, a handful of planets, a tiny fraction of even the nearest stars, at least one other world besides Earth shows evidence of biology, and from that we could begin to infer something real about the probability of life. The implications for astrobiology as a discipline would be enormous. The field would transform overnight from a science built largely on theoretical speculation, an Earth-based analogy, into an empirical science with actual data points from multiple worlds. The questions we would be able to ask would sharpen dramatically. Instead of, does life exist elsewhere, we could begin to ask what are the chemical and environmental conditions that favour life's origin and persistence, and actually have more than one example to work with. Every single theory about the origin of life would need to be re-examined in the light of the K2-18b context. Does RNA world work in a hydrogen-rich ocean? Does hydrothermal vent chemistry operate differently under Hycean pressure conditions? What mineral surfaces are available at the base of a Hycean ocean to catalyse prebiotic reactions? These questions would generate decades of research, laboratory experiments, theoretical modelling, and the search for additional biosignature detections to expand the dataset further. The discovery would also profoundly affect our understanding of evolution. Life on Earth has diversified into a staggering array of forms over 4 billion years, but all of Earth's life shares a common ancestor and a common biochemical framework, the same genetic code, the same basic molecular machinery, the same fundamental metabolic strategies. Life on K2-18b, if it exists, would have evolved independently, in a completely different chemical environment, over what might be a completely different timescale. Whether it would use anything recognisable from Earth's biochemistry, whether it would be DNA-based, carbon-based, water-dependent in the same ways, is genuinely unknown. It might be biochemically similar to Earth life, suggesting that the constraints of chemistry converge on similar solutions across different environments. Or it might be radically different, suggesting that life's molecular basis is more contingent than we think, that there are many possible biochemistries, not one inevitable one. We can't answer any of these questions from spectroscopy alone. DMS in an atmosphere tells us that something is producing it, but it doesn't tell us what that something looks like, how it's organised, what its genetic material is, whether it has cells. The gap between this planet has dimethyl sulfide in its atmosphere and we understand the biology of K2-18b is vast. It might be the work of generations of scientists, assuming we never find a way to send anything to that system and study it directly. But the first step, confirming that something is there, is where we are right now, tentatively, cautiously, with one hand on the door and no certainty about whether it will open. Chapter 18. The strange case of the vanishing signal. We've talked extensively about what the DMS signal is, how it was detected, what it might mean, and why it's variable. But we haven't fully reckoned with what might be the strangest and most profound aspect of the entire K2-18b story. The possibility that the signal is not just variable, but that it has genuinely weakened. That something which appeared to be there in the earlier observations is, in the most recent data, diminished, faded, retreated. The 2025 paper is careful about this. The language is measured. They don't say the signal has disappeared. They say it has shown a marked reduction in prominence in the most recent observation epoch. That's a different claim. A claim about change over time, not about absence. But it's a claim that opens up interpretive possibilities that are, depending on your perspective, either deeply troubling or deeply fascinating. Let's consider the possibilities seriously. If the DMS signal is biological and it has genuinely weakened, what could that mean? The most immediate biological interpretation, the one analogous to Earth, is that a bloom has collapsed, that whatever ocean organisms were producing DMS in large quantities have died back. Phytoplankton blooms on Earth are transient phenomena. They arise when nutrients are available and light is sufficient. They collapse when nutrients are depleted, when grazing pressure from zooplankton increases, when light conditions change with season, or when the physical mixing that brings deep nutrients to the surface slows. After a bloom, the ocean surface can look almost lifeless for weeks or months before conditions recover, and a new bloom begins. A similar dynamic on K218b, if it exists, would produce exactly the pattern the observations seem to show. A period of high biological productivity, detectable through elevated atmospheric DMS. A collapse. A period of low productivity and low DMS, potentially followed by a recovery. The observations have not yet covered a long enough baseline to see whether the signal cycles, whether a new bloom episode will appear after the current quiet period. That's one of the things the proposed follow-up observations are specifically designed to look for. But there's another biological interpretation that is less comfortable and more speculative, and that the title of this video is gesturing toward. What if the reduction in the signal reflects not a temporary bloom collapse, but a more significant change in the biology of K218b's ocean? What if something happened, a catastrophic change in ocean chemistry, a mass extinction event, a shift in the ecological balance, that has reduced the overall productivity of whatever organisms are producing DMS? Planetary scale mass extinctions have happened on Earth. 5 of them, at least, that we classify as major. Events that eliminated between 70 and 96% of all species alive at the time. The end-Permian extinction, approximately 252 million years ago, came close to wiping out all complex life on Earth. It was probably caused by a combination of factors: massive volcanic eruptions releasing enormous quantities of CO2, ocean acidification and deoxygenation, disruption of food chains from the base up. In its aftermath, atmospheric oxygen levels dropped. The chemical signatures of life in the environment changed dramatically for millions of years. We cannot see K218b's biology in this kind of detail. We cannot distinguish between a phytoplankton bloom collapse and a mass extinction event from a few data points of atmospheric DMS concentration. The timescales are too different, and our temporal resolution is too coarse. But the possibility that we're observing a changing biological system, not a static one, is real, and it's one of the reasons why follow-up observations have such urgency. If the signal is genuinely declining over time rather than cycling, that's a very different situation from seasonal variability. There is also a deeply humbling interpretation that needs to be stated plainly. What if we arrived too late? What if K218b had a biosphere that was robust and productive, that would have been unmistakably detectable, that would have shown DMS concentrations strong enough to be detected at 5 sigma confidence? But that is now in its twilight. Life on any planet is not guaranteed to persist. The sun will eventually make Earth uninhabitable. K218 star, being cooler and dimmer, will outlast our sun by billions of years in its main sequence phase. But other catastrophes could end a biosphere. Massive asteroid impacts, volcanic super events, runaway glaciation or warming triggered by slow changes in atmospheric composition. If K218b's biosphere is in decline, if the ocean organisms that once produced abundant DMS are dwindling toward extinction, we might be observing the fading signal of a living world that is, in geological terms, already mostly gone. This is not a scenario we can currently distinguish from others. It might never be possible to distinguish it from what we can observe remotely. But the fact that it's on the table, that we might be watching the last flicker of life on another world, is itself a profound and unsettling thought. It would mean that we found what we were looking for, and found it just in time to watch it disappear. Or perhaps not in time at all. Perhaps we arrived too late, measuring the echo of a biology that peaked millions of years ago, and has been declining ever since, still detectable, barely, but on its way out of a universe that will not mourn it, because there is no one else out there to do the mourning. That possibility should make us think carefully about how we treat our own biosphere. The only one we know for certain is alive. Chapter 19. The Road from Here. James Webb is a finite instrument with a finite lifespan. Its mirror doesn't degrade in space the way Hubble's did. There's no atmosphere to deposit contaminants, and the gold coating on the mirror segments is extraordinarily durable. But Webb's operational lifetime is limited primarily by its fuel supply. The telescope uses hydrazine fuel for station keeping, small thruster burns that maintain its position at L2 against the gravitational perturbations that would otherwise gradually push it off course. The fuel supply that Webb carried at launch, thanks to the extraordinary precision of the Ariane 5 rocket that delivered it to nearly its target orbit, is expected to support operations for approximately 20 years from launch, which means Webb has, as of 2025, roughly 17 years left. 17 years is a long time in science, but it's not infinite, and the questions that K2-18b has raised, questions that require sustained, repeated, long baseline observations to answer properly, will demand a significant fraction of Webb's remaining lifetime if they're to be answered at all. This creates a prioritization problem of genuinely historic proportions. Webb is oversubscribed. Every year, astronomers from around the world submit proposals requesting far more observing time than the telescope can provide. A large committee of scientists reviews those proposals and allocates time based on scientific merit. K2-18b is, by any reasonable measure, one of the highest merit targets in Webb's entire observing program. The scientific return from continued observations is enormous, given the stakes of the question, but it competes with equally compelling science. The first detailed studies of galaxy formation at cosmic dawn, the characterization of black hole environments, the investigation of the solar system's outer bodies, the atmospheric studies of dozens of other planetary systems. The K2-18b team's ability to secure sufficient Webb time to definitively answer the DMS question will shape the pace and completeness of the science. If they get the time they need, if the time allocation committees recognize the historic nature of what might be at hand, the DMS question could potentially be settled within the next 5 years. If time is constrained, the answer might come more slowly, in fragments, one ambiguous observation at a time, stretching out over a decade or more. Meanwhile, the next generation of ground-based observatories is coming online. The extremely large telescope being built by the European Southern Observatory on the Cerro Armazones mountain in Chile will have a 39-metre primary mirror, far larger than any existing telescope. First light is expected around 2028. The ELT will not be able to conduct transmission spectroscopy in the same way Webb does. It can't see above the Earth's atmosphere, which absorbs many of the infrared wavelengths relevant to atmospheric biosignature detection. But it can do high-resolution spectroscopy from the ground at wavelengths where the atmosphere is transparent, and its enormous light-collecting area will enable it to characterize exoplanet atmospheres in ways that complement rather than replicate what Webb does. Combined Webb and ELT data on K2-18b, covering different wavelength ranges, using fundamentally different measurement approaches, would provide the kind of multi-technique cross-check that makes biosignature detections much more robust. Further in the future, NASA is in the early stages of developing the Habitable Worlds Observatory, a mission specifically designed to directly image Earth-like planets around Sun-like stars and characterize their atmospheres. With unprecedented detail. HWO is a long-term project. Its launch date is not likely before the mid-2040s, but it represents the recognition that Webb, as transformative as it is not the final word. The search for life on other worlds requires sustained investment across multiple generations of instruments, each more capable than the last, each providing new vantage points on a question that may ultimately require all of them to answer. K2-18b itself will be studied again and again in the years ahead. Its 33-day orbital period means that Webb can observe multiple transits per year. Each additional transit observation adds to the statistical power of the DMS detection, clarifies the variability pattern, and constrains the atmospheric model. A program of sustained monitoring, observing K2-18b through every feasible transit for the next several years, would generate a dataset whose statistical power would eventually be sufficient to either confirm or refute the biosignature hypothesis at a level of confidence that the scientific community could accept as definitive. That's the road from here. Long, slow, filled with uncertainty at every bend, but navigable with the tools we have and the tools we're building, and leading, somewhere ahead of us, to an answer. Chapter 20. What this moment actually is. We need to be honest about something as we approach the end of this story, and honest means acknowledging the full complexity of the situation, not just the excitement, not just the caveats, but what this moment actually represents in the long arc of human inquiry. We have not discovered life on another world. That needs to be said clearly. The DMS detection on K218b is tentative. It has not reached the 5 sigma confidence threshold that scientists require for definitive detection claims. It has not been independently confirmed through multiple observational techniques at the level needed to eliminate alternative explanations. It is not proof of life. It is not even near proof. It is a scientifically credible suggestion, an intriguing pattern in the data, a hint that is stronger than a rumour but weaker than a fact. But it is also more than nothing, significantly more, and understanding what it is, precisely what it is, neither inflated nor deflated, requires holding 2 things in your mind simultaneously. On one hand, the caution, the history of false positives, the systematic errors that lurk in every complex measurement, the very human tendency to see patterns that aren't there, to interpret ambiguous data in the most exciting way available, to want this to be true so badly that the wanting subtly distorts the seeing. These are real dangers. They have led real scientists astray before. They must be taken seriously every single time. On the other hand, the genuine novelty. The fact that we have, for the first time in human history, an instrument capable of detecting the molecular signature of biology on a planet orbiting another star. The fact that that instrument, pointed at a world 124 light-years away, has returned data that is consistent with, and in the current state of our knowledge, more readily explained by, biological activity than by any known abiotic process. The fact that the scientific community is taking this seriously, not because it wants to believe, but because the data, carefully examined by multiple independent groups, continues to resist the alternative explanations that rigorous science demands we test first. Both of those things are true, at the same time, in the same result. This is what science at the frontier actually looks like. Not clean certainty, not dramatic revelation, but this, a tentative, contested, urgently investigated pattern in data collected from the edge of what our technology can achieve, pointing towards something that might be the most important thing we've ever found, requiring more work before we can know whether it is. And what is this moment in the longer story of human understanding? It is perhaps the moment when the search for life on other worlds stopped being a purely theoretical exercise and became an empirical one. When the question, is there life elsewhere, stopped being purely philosophical and started being scientific in the most direct sense, testable, measurable, with data that constrains the answer even if it doesn't yet determine it. That transition from speculation to measurement is one of the most significant transitions a scientific question can make. For centuries the existence of other worlds was speculative, then Kepler made it empirical. For decades, the composition of exoplanet atmospheres was speculative. Then Hubble and Spitzer made early inroads, and Webb made it robustly empirical. And now, for the first time, the presence of biological chemistry on another world, which has always been the most speculative of all these questions, is being addressed empirically, with data, with spectra, with molecules. We're not at the answer, but we are for the first time in the domain where the answer lives, and that's genuinely new. That's a genuine milestone in the history of science and the history of our species' relationship with the question of our cosmic loneliness. Chapter 21. The Silence and What It Means. Let's end with the thing the title points at, the signal that appears to be there and then seems to vanish, the DMS feature that was stronger in earlier observations and weaker in the most recent ones, the biology, if that's what it is, and that bloomed and then went quiet. There is something philosophically resonant about this pattern that I don't want to pass over too quickly. Because whether or not K218b turns out to harbour life, the experience of studying it, of seeing something appear in the data and then seem to recede, of chasing a signal that flickered and then dimmed, captures something true about the search for life in the cosmos. We look, we think we see something, we look again, more carefully, and the universe offers us just enough to keep us uncertain, just enough to justify the next observation, never quite enough to be sure. This could be an epistemological limitation, the inherent difficulty of knowing from this distance, with these tools, what is happening on a world we can never visit. Or it could be something else, something about the nature of life itself, that it is inherently dynamic, variable, pulsing with activity at one moment and quiet the next, driven by rhythms and cycles that a snapshot cannot capture. Life is not a static chemical signature, it's a process, a continuous energy-consuming, entropy-fighting process that rises and falls with the availability of resources, the pressure of competitors, the changing of conditions. Life blooms, and life fades, on Earth and possibly on K2-18b and possibly on worlds we haven't yet pointed our telescopes at. It waxes and wanes with seasons and ecological dynamics and evolutionary pressures that are entirely internal to the living system, invisible to any external observer who cannot see the ocean beneath the atmosphere, who can only read the chemical aftermath of what the ocean breathes into the sky above it. To search for life across 124 light-years and find a signal that comes and goes is, in a strange way, exactly what you should expect if life is what you're looking at. Geology doesn't pulse like that. Chemistry, in the absence of biology, doesn't bloom and retreat on timescales relevant to observational astronomy. The variability itself, not just the detection, but the change in the detection, might be the most biologically diagnostic thing about what Webb has seen, or it might be noise. And this is the tension we live with. This is where science leaves us right now, at this moment in 2025. Uncertain, engaged, unable to look away. The James Webb Space Telescope continues to orbit the L 1.5 million kilometers from Earth, its golden mirror segments aligned to better than a fraction of the wavelength of light, its detectors cooled to within a few degrees of absolute zero, its reaction wheels spinning steadily, its data streaming home. It will observe K2-18b again, and again. The data will accumulate, the models will improve, the laboratory experiments will produce results, the independent analyses will converge or diverge. And somewhere in that accumulation, perhaps in a paper published 2 years from now, perhaps 5, perhaps 10, there will be a moment of clarity, a point where the evidence taken together says something definitive. Either, yes, this is real, this is biological, this is the signature of life on another world, or no, this was an artifact, a coincidence, an abiotic process we hadn't modelled correctly, a reminder of how careful science must be when the question is this important and the wanting is this powerful. Either answer will matter, either answer will change us, because we will have learned something fundamental about the universe we inhabit, about whether the quiet of the cosmos is populated with silent living things, or whether we are genuinely, in some deep and irreversible sense, alone. And if we're alone, if it turns out that the signal on K2-18b was noise and every other planet we examine in the years ahead returns the same empty chemistry, the same abiotic signatures, the same silence, then we will need to confront what that means, the full weight of it. That in this galaxy of 400 billion stars on whatever fraction of their planets has ever had the right conditions, life arose exactly once, here, on this small, rocky, oxidized, biologically drenched world, and that everything we are, every thought, every emotion, every piece of music and mathematics and literature and science, is the universe's singular experiment in knowing itself, irreplaceable, cosmically precious, alone in a way that should fundamentally alter how we treat the only living world we know. And if we're not alone, if the signal holds, if the follow-up confirms it, if K2-18b joins Earth in the census of living worlds, then we will need to confront what that means too, the full weight of it in the other direction, that life is a feature of the cosmos, not a bug, that the universe generates it wherever it can, that we are part of something larger than a single species on a single world, part of a pattern, a tendency, a fundamental creative drive built into the physics and chemistry of reality itself. Both of those possibilities are extraordinary. Both of them deserve the full seriousness of our attention. Both of them begin here, with a telescope pointed at a red dwarf in Leo, watching a small planet cross in front of its star, measuring the ghost of a molecule in a sky we will never stand beneath. The signal appeared, and then it seems to have faded. But the question it raised has not faded at all. It has never been louder, and the search that it has reignited, careful, rigorous, urgent, humble, is the most important thing our species is doing right now. We are looking for ourselves in the cosmos, and for the first time, the cosmos might be answering back.